Honorable Sir M.D. Abdul Raja for giving me such an opportunity to represent some important topics. I am Jannatul Mawa Trishna. My ID is 16051. I am the member of Team 6. My other team member introduced themselves in a perfect time. Today, our team present here to represent an effective presentation in basic concept of heat transfer. Now I am starting my presentation. Change please. Now we clearly show our table content. Here is a 13 topics here. First 4 I will briefly discuss. My topics is introduction of heat transfer, different modes of heat transfer, conduction and convection. So first of all, we see a question. The question is, what do you mean by heat transfer? Actually, heat transfer is the process of heat from high temperature object to a lower temperature object. In a heat transfer process, we need two objects. And the heat transfer can also take place within the system due to the temperature difference at various points inside the system. And I mentioned some application, the heat transfer in human body, heat transfer in water molecules, heat transfer from electric oil, etc. Now we show that there are different modes of heat transfer. Actually, we know that there are 3 modes of heat transfer. One is conduction, convection, and radiation. In this figure, we clearly show the 3 processes. There are 3 processes lay between one figure. The conduction, convection, and radiation occur simultaneously. Change please. And my other topic is conduction. What is conduction? Actually, the process in which heat flow from object with higher temperature to object with a lower temperature, this is called conduction. Conduction occurs in solid, liquid, or gaseous medium. So we need 3 medium for conduction process. Some example is silver, copper, iron, aluminum, etc. In this figure, we show three figures. One is for solid, other is for liquid, and other is for gases. So first, previous page, please. In solid figure, there are intermolecular spacing is not presented here. Actually, there is no intermolecular spacing is solid. And in liquid, there are some intermolecular spacing, and gaseous mediums, there are a huge amount of intermolecular spacing. Although solid, liquid, gas are important or knew properly of this conduction, but solid is more appropriate for conduction systems. Change please. And my last topics is convection. Actually, what do you mean by convection? Literally, the transfer of heat by the circulation of current from one region to the another, fluid or liquid or gas, this is called convection. So in this convection system, we do not need any solid medium. We only need liquid, gases, or fluid medium. Convection occurs in a large scale in atmosphere, oceans, planetary mass. Some example is oil convection. So in this figure, it is very important figure. Figure shows us a pot with full of water. The water molecule absorb heat. So first of all, the lower molecule absorb heat and they going to upward, and upper molecule absorb heat and they going downward. And full molecule of this pot of water can absorb appropriate amount of heat. So my presentation is in here. So thank you so much, sir, and thank you everyone for listening my presentation. Then I swift this presentation our next team member, Araf Mahmood. Thank you.
I am Araf Mahmood. My ID is PHY 16005. I am a team member of Group 6. At first, I thank our honorable teacher and for giving me the better opportunity and present present our main topic, the basic concept of heat transfer. My first topic is type of convection. I hope we are all well in the almighty of grace of Allah in this pandemic situation. Now I start my sharing this presentation. My first topic is types of convection. We know our first participant the basic explain this convection. Now I add a little bit. Convection, this means heat transfer in liquid and fluid. This is called convection. These processes are two types. One is natural convection and other is forced convection. My first topic, my first convection is natural convection. Natural convection, what do you mean by natural convection? Natural convection means this convection takes place in a fluid which is still rest, and heat transmitted from surface to still air is known as natural convection. The calculation of natural convection in this equation, we see that where H alpha is unbound convection coefficient. This is called unbound. This means there are no external force is needed. This is a good example of natural convection is upward flow to air due to the fire or hot object is the good example for natural convection. The another is forced convection. Forced convection occurs between the unbound surface. That means externally controlled. In this case, this forced convection was first invented by scientist MC Adam in this following relation, where V is the velocity of wind, and this convection is transfer coefficient is related to the wind speed. If we don't understand in this forced convection, then we as a perfect example, we now need perfect example of forced convection. Our home service has a ventilation system. Ventilation system, this means when our home inside the room is very hot, then we need to this hot air move out to the inside out. That means we are now externally forced, and this force air move inside this air directly move out in the outside. That means forced convection. Heating or cooling parts of the body by blood circulation, this is one of good example of forced convection. Our next topic is radiation. This is what is radiation? Why is it is called radiation? We everybody know radiation is the process of emitting energy through medium or space in the form of waves or particles. In this figure, one radioactive atom, their heat energy is transmitted in the form of waves and particles. In this radiation, this energy, but heat transfer process, what do you mean by radiation? Radiation is when two bodies are separated, when two bodies are at different temperature and separated by distance, then the heat transfer process between them is called radiation of heat transfer. In case of heat transfer, heat transition in the form of waves or particles. Such waves are some kinds of radiation are here. There are called electromagnetic radiation. What is electromagnetic radiation? There are some kinds of electromagnetic radiation. These are microwaves, waves, infrared, visible light. That is particle radiation such as alpha radiation, beta radiation, gamma radiation. And another is acoustic radiation. That means sound radiation, ultrasound radiation. Another radiation is gravitational radiation. These are always some kind of radiation. Now we are briefly now discuss our three modes of mechanism: conduction, convection, radiation. How we detect these separate kinds of mode of heat transfer. Now so we know the three basic difference between the three modes of heat transfer. The one is conduction, two is convection, and last is radiation. In conduction process, we know that the heat transfer is directly physical contact, where the convection directly physical contact, but there is a various kind of motion of fluid, or it's a liquid or gas, but solid is not exist. In radiation, heat transfer through electromagnetic radiation. Second is heat follows in conduction process. Heat flows from high temperature region to low temperature region, where the convection flows low density region to high density region. And radiation, it occurs at a bodies at temperature above 0 Kelvin. Third is convection. Conduction is in solid medium, only solid, but we know that convection occurs solid, liquid and gases, but mainly conduction occurs in solid medium, where the convection occurs only liquid or gaseous medium. Solid medium does not exist. And the radiation does not need any medium. That means in radiation process there is no medium needed. Where conduction is a slow process, and the convection is extremely slow process than the conduction. And radiation it propagates at the speed of light. That means it exists a very high speed. That means what is equal to or simultaneously equal to speed of light. Thank you for listening my presentation. I sweep my presentation in this section. Our next participant, MD Nurnobi Mondol. Nurnobi আছে?
All is well in this pandemic situation. Thank you so much, sir, to create a beautiful presentation environment. I hope it will be a lot of helpful for us in our practical life. So time is very short. Let's welcome to my presentation. I am Nurnobi Mondol, ID Physics PS 16055. I am team member of Group 6. I will try to discuss about 3 topics in this chapter: basic concept of heat transfer. Number 1, heat transfer equation in case of conduction. Number 2, heat transfer equation in convection. Number 3, heat transfer equation in case of convection. Heat transfer equation in case of conduction. First of all, the heat transfer equation in case of conduction, the rate of conduction can be calculated by the following equation: Q equal K into A, T hot minus T cold divided by T, where Q is the transfer of heat per unit time, K is the thermal conductivity of the body. You might say, what is the thermal conductivity, right? The thermal conductivity of a material is a measure of its ability to conduct heat. The equation where A is the area of heat transfer, T hot is defined by the temperature of the hot region, and T cold is the represent the temperature of the cold region, and D is the thickness of the body. Number 2, heat transfer equation in case of convection. It is represent the equation. The equation to calculate a rate of convection is follows: Q equal AC into A TS minus TF, where Q is the heat transfer per unit time, AC is the coefficient of convection heat transfer, and A is the area of heat transfer. Where the equation Ts is the surface of temperature, and Tf is the fluid temperature. Number 3, heat transfer equation in case of conduction. The rate of conduction can be calculated by the following equation: Q equal K into A T hot minus T cold divided by D, where Q is the transfer of heat per unit time, K is the, sorry, আমি
এটা হবে রেডিয়েশন আসবে তো মনে হয় নেটের জন্য পরে গেছে পরে
calculated by P equal E into sigma into A TR minus TC to the power 4, where P is the net power of radiation, A is the area of radiation, TR is the represented by radiator temperature, and TC is the surrounding temperature, and E represented by emissivity, and sigma is Stephen constant. You might say, what is emissivity? Actually, the emissivity of the surface of a material is effectiveness in emitting energy as thermal radiation. Another Q sigma is Stephen constant. You might also say, what is the Stephen secant? I can say that the Stephen Boltzmann constant SI unit sigma equal 5.670 গুণন 10 to the power 8 Weimar per square Kelvin to the power K to the power minus 4. Here is my presentation in my team member Junaid Bagdi. I request to you discuss about another topic in this chapter. Thank you so much. Assalamu alaikum.
ID H16008, member of group number 6. Now let us talking about the topic. In this previous section, my group member MNN Mondal talking about heat transfer process through conduction, convection, and radiation. In this section, I'm talking about heat conduction through different surfaces. So I'm taking 3 steps here to describe about different surfaces for heat conduction. Now for the first item, heat transfer process in flat plate collector. First of all, we know that rate of heat transfer is proportional to the area of transferring surface and temperature gradient. So it is equal to Q dot is equal to A into dt by dx. For the proportionality is kept, I get that Q dot is equal to K into A into dt by dx, where K is the thermal conductivity. Now, let us see in the topic. In this figure, we see that a flat plate collector, where a flat plate collector, where we see that from the first equation, I told that Q0 equal to K into A into dt by dx. Now formulate this equation. Formulate this equation, we get that dt by dx equal to Q dot by A by K. Then I integrate this equation and take and get equation and take a boundary equation from the surface. Looking at the picture, what I see that heat flow in the flat plate collector, where for the boundary condition we take T equal to T2 at x equal to 0 and T equal to T1 at x equal to L. For applying boundary condition and integrating this equation, we get that Q0 equal to K into T2 minus T1 by L. So that is the heat transfer process in the flat plate collector equation. Here, Q equal to the total amount of heat, K equal to heat transfer coefficient, A equal to area of the surface, L equal to length of the plate, T2 equal to temperature of the hotter surface, and T1 equal to temperature of the cooler surface. Now, let's take up the next item. Turn over, please. Conduction through in concentric cylinder. From the first previous section, I'm talking that Q dot equal to K into A into dt by dx. So, where A is the area of the surface. Look at the concentric cylinder. In this one concentric cylinder, for area A, we get A equal to 2 pi RL. So take this equation and putting this value on those first equation and formulate the equation and integrating that, where after the integration we get that QL equal to UL into T in minus T out. It is the heat conduction through in concentric cylinder equation. Here, look at the picture. We see that R in is the radius of the inner surface of the cylinder, R out is the radius of the outer surface of the cylinder, T out is the temperature outer surface of the cylinder, and T in is the inner surface, inner temperature of the cylinder. So from integrating those and taking this limit, we get this equation QL equal to UL into T in into minus T out. Here T in is always greater than T out. Now that is the heat conduction through in concentric cylinder equation. Now here, when a number of concentric tubes are used, the overall UL average value UL bar is given by 1 by UL bar equal to 1 by UL1 plus 1 by UL2. So when we take the average value, we taking the UL term, average term. So QL, so last of all, we get that QL equal to UL average or UL bar into T in minus T out. So that is the heat conduction through in concentric cylinder equation. Now look at the third topic, that is about heat conduction equation in a long cylinder. Look at the picture. Here it is the one-dimensional heat conduction through a long cylinder. I think that is a very long process. So I'm talking about this process. Here see in this picture, Q dot R plus del R, that is the rate of heat conduction at R plus del R. And see that Q dot R, that is the rate of heat conduction at R. And also we see that Z dot. What is this? It is the rate of heat generation inside the element. So for a little, for a small amount of temperature, we get equation that rate of heat conduction at R minus rate of heat conduction at R plus del R plus rate of heat generation inside the element equal to rate of change of the energy content of the element. So we get that from this figure and this equation that Q dot R minus Q dot R plus del R plus G dot element equal to del E element by del T. So that is the for a little small temperature we get this equation. Now in this from this equation we compare this equation with the Fourier law of heat conduction. From compare this we get a final equation, that is the heat conduction equation, a long cylinder equation. We get that 1 by R into del by del R into R A into del T by del R plus Z dot plus rho C into del T by del small t. So that is the heat conduction equation in a long cylinder. So there is some term for variable conductivity and constant conductivity. For variable conductivity, we change some term. Here we see that 1 by R into del R into K is the changeable term into del T by del R plus Z dot equal to rho C del T by del small t. What C is the specific heat we know. So there is the variable, for this reason there is the variable conductivity term, and for the case of constant thermal conductivity the equation above reduced to